As massive globalization perpetuates, the deterioration of our air due to greenhouse gases has become a pressing concern to us. Air pollution has long been directly tied to congestion levels in cities, and it is no surprise today that cities with high congestion levels have also high pollution levels. At the Paris Climate Conference in December 2015, 195 countries adopted a universal climate deal which sets out to limit global warming to well below 2 degrees. The agreement is due to enter into force in 2020 and will force authorities around the globe to rethink their national climate policies. As nations undergo heavy urbanization, not only do governments have to think about their carbon footprint, but also the efficiency of their road networks. Dynamically optimizing both traffic and air quality across the country are tough and conflicting objectives, but can be tackled with the power of computing. Traffair aims to mitigate traffic congestion while meeting air quality standards by providing a smarter traffic management system based on air pollution levels across large cities. The Traffair system is based on a research project called iTrack from the De Montfort University, which gathers space data about greenhouse gases, meteorological information, and traffic levels to develop a statistical model that creates a navigation algorithm. We wanted to use data acquired on the ground to build a model that could predict the level of traffic at various locations based on their levels of nitrogen dioxide. When preparing for the project, we first investigated where to find the data to build our statistical model. We used the London Air API and the Here Maps Traffic API to gather data about nitrogen dioxide and traffic levels at various locations in London. Then, our hardware investigation concluded that the Raspberry Pi was the most suitable controller for nitrogen dioxide sensors. We kept the investigation of data analysis tools until a later stage, when we had gathered enough data. Traffair is powered by Watson's Predictive Analysis API, which offers real-time traffic level prediction based on statistical models built in SPSS. We concluded our design and preparation phase by establishing a strict timeline that would guide our development cycles and our meetings. This is Traffair's architecture. It uses public data to build the computational intelligence module, which provides statistical models used to predict traffic. When real-time data arrives from the sensors deployed in the wild, the traffic prediction module queries the statistical model to get traffic predictions. Once all the location's traffic levels are estimated, the routing algorithm provides the optimized path for the traffic lights to abide to. This real-time data is then available on a user-friendly monitoring dashboard and through a public API that allows anyone to integrate with the Traffair system. Traffair is built with Raspberry Pi and nitrogen dioxide sensors connected to the cloud computing platform, which acts as the computer intelligence, traffic prediction, and routing modules. It is powered by IBM Bluemix and Node-RED, where the data gathering, the statistical, and the prediction models are hosted. The statistical model is built with IBM SPSS Modeler, based on the data gathered over 2 weeks period from the London Air API and the Here Traffic API. This SPSS model is then uploaded to Watson's Predictive Analysis service and used in Node-RED as an API to predict the traffic levels. All of the predictive information is beautifully outputted in a user-friendly monitoring dashboard and also available as a public API. We then used Excel and MATLAB to perform offline analytics on the comparison between our prediction and the actual measured traffic levels.